were discussing about the continuity equation last time, and let us work out a problem from your textbook to go ahead. So, we have a nozzle like this, and it is carrying a fluid with density equal to constant, and some other input data are given for the problem. The area of the cross section of the nozzle, it varies with the area of the cross section of the inlet in the following manner. Where x is the coordinate measured from the entrance, and other information that is given, that the velocity at which the fluid enters the nozzle, let us say that is u infinity, that varies with time. So, it is of the form of c into 1 plus at, where these a naught, b, c, a, these are some given numbers, and these are dimensional parameters to adjust the dimensions of the expressions. What we are asked to find out, that what is the acceleration as a function of x. One important assumption is density equal to constant. The other assumption that may not be stated explicitly in the problem, but we will assume to go ahead, is that it is an inviscid flow. So, when we assume it as an inviscid flow, that means we are not bothering about the variation of velocity along the transverse direction. We are assuming that at each section the velocity is uniform. Now, to find out the acceleration, we have to go step by step. We have to first find out what is the velocity. How do we find out the velocity here? If you are given these information, how do you find out the velocity? Say u at a given x, how do you find that out? You know the u at x equal to 0, you know the a at x equal to 0, you know the a at some given x. So, you can relate that with u at a given x through the integral form of the continuity equation. So, if you take a control volume like this one, maybe where say this distance is x. So, here the area A is a function of x, and how do you express u infinity in terms of u at x? See, in this control surface, the surfaces which are the lateral surfaces across which there is no flow. So, only flow is through the inlet and through the surface at x. So, you can write from the continuity equation, it is density equal to constant. So, it is as good as u infinity into a naught is equal to u at x into a at x. As we discussed earlier, this u should have ideally been the average velocity at that cross section, but because it is uniform, it is same as at the center line, there is no difference. So, you can find out what is u at x, that is u infinity a naught by a at x. So, that is u infinity divided by 1 minus bx, because a naught by a is 1 by 1 minus bx. You have to also keep in mind that u infinity is not a constant, but it is a function of time. So, it is c into 1 plus at divided by 1 minus bx. Once you know that what is u as a function of x, the next thing that you can do, you can utilize the expression for acceleration. So it is not only a function of x but also a function of time. So the remaining work is very straightforward, that acceleration along x it is just a one dimensional type of flow, but u here we write it is not just u as a function of x but it is also a function of time. So here we write it u x t to be more precise, because at a given x it will also vary with time, and then you can differentiate this expression. That is a straightforward exercise to find out the acceleration component along x. There is no acceleration along any other direction, because it is just a one dimensional flow. So here you can see an example where you have both the temporal component as well as the spatially varying component of the acceleration. So given this acceleration, it is also possible to find out that how much time a fluid particle will take to traverse, say, from one end of the nozzle to the other, or given in fact the velocity components or just here one component of velocity, you may work out that what should be the time necessary for a fluid particle which is injected here to move along the center line from one end to the other, if you know the velocity component. So it is just like tracing the path line and finding it out when along that path it moves and comes to the end of the channel. So that is a straightforward extension of this one. Okay. So we will move on to our next concept, and that concept is related to the angular deformation of the fluid elements. So till now we have discussed about the linear deformation of the fluid elements, and from the linear deformation of the fluid elements we found out that we got as a consequence a very important equation known as the continuity equation. For the angular deformation, we will try to first sketch that how a fluid element when deformed angularly will look, and then try to quantify it in terms of the velocity components. So angular deformation of fluid elements. Let us say that we start with a rectangular fluid element like this. When we are thinking about angular deformation, the deformation is in terms of change of an angle, and that angle change may take place in a plane. So although the general fluid element is a 3-dimensional element, but you can always take a 2-dimensional element and consider the deformation in the plane, because no matter how complicated the deformation is, it may be resolved in different planes. So let us say that this is one such plane in which the deformation is taking place. So what is this special plane? This is an xy plane. So for example, if there is a rotation with respect to the z axis, then that occurs in this plane. So it does not mean that if we are focusing our attention on a plane, we are actually restricted to 2D. We are actually restricted to one component of the deformation, and other components will be very similar. Let us say that name of this fluid element is ABCD, and it has its dimensions, say delta x and delta y along x and y. Now let us stretch our imagination and assume that this fluid element has got deformed with time. When it has got deformed, it is possible that it has got deformed in two ways. One is its volume might have got changed, which is like an extension of the linear deformation, but its shape might have also got distorted, which is more common if it is under shear. So, if its shape is distorted, let us say that maybe it has come to this shape. This may not be a very regular shape, this is just a schematic. So, now if you see that what are the important parameters that are characterizing this deformation. If you draw two lines through this new location of A, say one along x and another along y, the first important parameter that will come very much apparent is this angle, say delta alpha. Here we are considering a small interval of time delta t within which this deformation has occurred, because if we allow a large time we will not be able to keep track of the deformation, fluid is under continuous deformation. So, we take a small time interval. In that small time interval the element AB, which was originally oriented along x, now is oriented at an angle delta alpha with x. Similarly, let us say that this angle is delta beta. Our objective will be to quantify the time rate of change of these angles, say alpha or beta, in terms of the velocity components, here u and v, because it is in the xy plane. To do that, we may make some simple geometrical construction. It is not actually a construction, but just to figure out what is happening. So, if you think of a right angle triangle like this, maybe A prime, B prime, E prime. This right angle triangle is important because in that right angle triangle, if you know that what is B prime E prime, then you may possibly be able to express delta alpha or tan of delta alpha in terms of that and A prime E prime. So, let us try to figure out what is B prime E prime, that is the next objective. To do that, we first understand, or we first try to figure out that what is the vertical displacement of the point A. See, to know B prime E prime, our consideration is the vertical component of the displacement. So, first we find out what is the vertical component of the displacement at A, also we find out what is the vertical component of the displacement at B. The net difference between these two is this length B prime E prime that we are talking about. So, what is this displacement? Let us say that the velocity at the point A is given by the two components u and v. U comma v are the components of the velocity vector. So, at A, if you allow a time of delta t, what should be the vertical displacement? V into delta t. Next we try to find out that what is the corresponding vertical displacement for the point B. So, if this is V, we have to find out what is V at B. So, V at A is V, what is V at B? That V we have to write here. So, what is that V? V plus higher order terms. So, here the change is because of change in x. So, that is why partial derivative with respect to x. So, from A to B when you go, it is not change in y but change in x. that is why this term is appearing, then that into delta t. So we can say that B prime E prime, that is nothing but the difference between these two. So that is like this. Similarly, what is A prime E prime? A prime E prime is like delta x plus some higher order term. It is not exactly delta x, but it is why it is not exactly delta x, because when the fluid element has got deformed, now this component along x gives the linear deformation along x. So linear deformation along x is something, it is not 0 in general, therefore it is not same as delta x, but it is actually delta x plus the change in delta x. So delta x plus the strain along x times delta x, and that is much smaller than delta x itself. So and we have figured out earlier that what is that. So if you go back to that, you will see that it is delta x plus some higher order term, that is the new length along x. So if you find out what is tan of delta alpha, then that is equal to B prime E prime by A prime E prime. So that will be like this, and maybe some higher order terms. So the delta x from the numerator and denominator, it has got cancelled out. It is like this is a negligible term. Remember, we are taking the limit as delta t tends to 0. So when you are taking the limit as delta t tends to 0, this higher order term is tending to 0, this higher order term is tending to 0, this higher order term is also tending to 0. So effectively in the denominator you are left with only delta x, in the numerator you are left with only this term, other terms are vanishingly small in comparison to this dominant term. So in that limit, now as we know that if we are allowing a very small time interval delta t, this angle delta alpha also will be very small. So in that case this tan delta alpha is as good as delta alpha. The conclusion from this expression is that we can write this with limit as delta t tends to 0. We have already taken that limit, but now we are just writing it more formally. Delta alpha divided by delta t is equal to the partial derivative of v with respect to x, and this is nothing but the rate of change of the angle of this line element with the horizontal. So let us call it alpha dot, that is partial derivative of v with respect to x. Similarly we can say that what is beta dot. So similarly, just by same consideration, what will be beta dot? It will be the partial derivative of u with respect to y. So whatever geometrical consideration you had on this side, if you have it on the other side, it will exactly lead you to the same thing. So we have got a quantification of the rate of change of these angles, and these are like rates of deformation, so to say. Now this rate of deformation we have to quantify in terms of certain parameters. So, when we quantify the rate of deformation, we have to keep certain thing in mind, that we have to give a definition to what is rate of deformation. These are just changes in angles. Now, how we translate that into a more formal definition? So, to have a more formal definition, we may say that we are defining the rate of strain or the rate of deformation in the following way. Rate of strain or angular deformation. In what way? See, there is a very important quantification of the distortion in the angle. What is that? If you consider two line elements, say AB and AD, they were originally at an angle 90 degree with each other. Now, these line elements are no more at an angle 90 degree with each other, they are now at an angle 90 degree minus delta alpha minus delta beta. So, this difference between 90 degree and this one gives an indication of the angular deformation, because if there was no angular deformation, this angle would have remained as 90 degree. So, what is the change in this angle? So, what is the speciality of this angle? We are trying to identify what is the change in angle between two line elements in the fluid which were originally perpendicular to each other. So, these are representatives of two line elements which were originally perpendicular to each other, but with deformation they are no more perpendicular to each other. So, what we are interested to find out, that what is the rate of change of angle between two line elements in the fluid which were originally perpendicular to each other. So, if we want to quantify that, we now know that we can quantify that in terms of delta alpha and delta beta, and the rate in terms of alpha dot and beta dot. So, what is the change? The change is pi by 2 minus pi by 2 minus delta alpha minus delta beta. So, it becomes delta alpha plus delta beta, that is the total change. So, the total rate of change is alpha dot plus beta dot. It is like delta alpha plus delta beta is the change, the rate of change is you divide those by delta t and take the limit as delta t tends to 0. So, this is nothing but okay. So, this we may call as say epsilon dot xy as a symbol, epsilon for strain, epsilon dot for rate of strain, xy to indicate that it is actually an angular strain in the xy plane. That is just a nomenclature, one may use of course different nomenclatures, but I mean this also works. In this way it is possible to write epsilon dot yz and epsilon dot xz. You see that specification of this epsilon dot requires two indices. So, what are the indices? The indices are the coordinate directions along which your original line elements were oriented, and now because of deformation those line elements are not oriented anymore along those directions. So, if you want to write it in an index notation, say if you want to write now it as epsilon dot ij, how will you write it? just think in place of I and x and y, I and j. So what will be this one? So this is the component of velocity along j. So partial derivative of uj with respect to xi plus partial derivative of ui with respect to xj. The advantage with this notation is now once you write it, you do not have to bother whether you are writing in xy plane, yz plane or xz plane. It is like you just replace I and j with the particular indices 1, 2, 1, 3, 2, 3 like that. One important observation that you can see is epsilon dot ij is same as epsilon dot ji, just replace I with j and j with I. So it is symmetric. So if you write it in the form of a matrix where you can see there are two indices, each index varies from 1 to 3, that means you can write a 3 by 3 matrix using these components. Again out of that you will have 6 independent components because of this symmetry. So this is written in a, this may be written in a matrix form, that is the components of this. Not only that, what is the other thing that you get from this? See, this is also a second order tensor, because it may be shown that it maps a vector onto a vector, and not only that, it requires two indices for its specification in the Cartesian notation. So we have seen the rate of angular deformation, but one important thing is we have seen examples earlier that there are cases when the fluid element is not having angular deformation as such like this, but it may be rotating like a rigid body. So if the fluid element is rotating like a rigid body without any angular deformation, then there also will be a change in some angle, that will not be an angular deformation but the change in angle because of rigid body rotation. So that is also an aspect of angular deformation, and in place of deformation we can just call it rotation, because it is not actually a deformation, it is the change in some angle because of a rigid body type of motion. So we will now see that what is the way in which we may parameterize or we may describe the angular velocity of a fluid element, and that angular velocity definition should be such that whenever there is a rigid body motion, the angular velocity will only be there but the rate of deformation will be 0. So keeping that generality in mind, we have to define the angular velocity. These are all definitions. We know that what we want to qualitatively represent, and we are now trying to put into some mathematical definitions to quantify those physical features. That is what is the exercise we are undergoing at the moment. So the next objective therefore is finding the angular velocity of the fluid element.